Respect the unstable, practice problems. So we start off with this transfer function system. Notice that it has a 0 in the right half plane, and it also has a pole, 2 poles at the origin, which is on the imaginary axis. We designed this controller, and we notice that PK has this transfer function. And we go ahead and close the transfer function. So this is the complementary sensitivity function. We get this, and we can see that I can factor the denominator this way and see that all the poles here are in the open left half plane. So this is stable. So if we compute the step response of the system, we notice that, boom, it does pretty nice. It has a little bit of overshoot, settles nicely to 1. Look at the control signal. Boom. Okay, so that's the signal down here. Boom, blowing up. Control signal's blowing up. So if we look at the 6 transfer functions for our system, we have, these are our 6 transfer functions. Notice this one's stable, this one's stable, this one's stable, this one's stable. Oh, that one is not stable. This one is not stable. So notice that the transfer function from R to U, from the reference input to the control signal, is unstable. Okay, it's unstable. So we clearly are going to have trouble. So this shows us that we do not have internal stability, even though most of these transfer functions are in fact stable. So if we reduce our set of controllers down to the 4 instead of the 6, we notice we still have this one over here that's associated with the instability. Okay, so we have this these 4 transfer functions, and we have that instability. For our next example, we have this is our plant. Notice that it has a 0 in the right half plane, and it has the plant has a pole at positive 1. Here's our controller. This controller has a 0 at positive 56, and it has a pole at the origin. So these are the Z's, these are the P's. So this is our set of right half plane zeros. This is our set of right half plane poles. Now, using this plant and this controller, we have this sensitivity function. Okay, this is the sensitivity function for our system. And notice I have 4 poles here, 4 poles here. The sensitivity function has 4 poles. There's no cancellation whatsoever. There's still 4 poles altogether, which means there was no cancellation altogether. So if I go through and I look, if I plug in for the values of Z, that is, I plug in 2 and 56. In both cases, when I do that, I will get, for wherever I see S, I will get 1. I will get exactly 1. Now, it's not obvious from the way this is, but if we actually multiply it out, I will get that. If I plug in 56 into here, I will get exactly 1. If I go through and I plug in 0 or 1 into this expression, notice that 0, if I plug in 0, I'm going to get something positive in the denominator. In the numerator, if I plug in 0, I'm going to get 0. Similarly, if I plug in 1 in the numerator and the denominator, I'm going to get all positive quantities, and in the numerator, I'm going to get 0. So I see that, in fact, I do have these conditions satisfied for this problem. So if we now look at the open loop magnitude of the product of these two things, this is what we get for our open loop magnitude. So notice that I have these spiky things, which are poles. So this is the Bode magnitude plot. But notice that those poles, here's the real axis. And so all of this is in the right half plane. And I see that my poles are not over there. Okay, I see my poles are not over there. Well, actually, let me take that back. I have a pole at the origin, and I have a pole at 1. So actually, so my open loop system has that. Sorry about that. If I look at the closed loop now, the closed loop poles and zeros, I can see that I will have 0 at the origin and 0 at this value, but the poles are strictly in the left half plane, and so the magnitude in the right half plane of this product of this transfer function, the magnitude is finite. Okay, it's strictly finite. So it's not maybe so obvious to look at it from this 3D perspective. If I turn it this way, so I'm actually looking along the real axis, I can see that I notice that near the imaginary axis, I'm very close to infinity, but I'm actually finite. So it's not that obvious to see, but that's what we have. Here's the next example. So this example is brought up by the author of the paper as an example to look at. In this case, we have an inverted pendulum. The pendulum has some mass, it has some length, and so we get these formulas for the dynamics. So here, notice that this is riding on top of a cart. So the cart has its dynamics, the pendulum has its dynamics, and so we have all the set of dynamics here. So this is y, in this case, is the horizontal position. Theta is the angular position of this, and so we have those two. So this is our these are our differential equations that describe the motion here. We can put it and create a linear model. This is our linear model. Notice that I have a column of zeros. That indicates that my system has an integrator, that a zero at the origin. And actually, if I look carefully, I can actually break this up into partition it into this block and this block along the diagonal. This block actually has two zeros. So this has a double integrator, or what's called a double integrator. That is two poles at the origin. Okay, and the other two poles, it turns out one of them is in the right, strictly in the right half plane. So this system definitely has some instability going on. So when we design a controller for the system, and I'm not going to show you the controller designs, they're kind of messy looking, but what I'm going to show you is the sensitivity function for the system using those four different stabilizing controllers. Here they are. Boom. There's the sensitivity function for the four different controllers. So notice that in general, again, the area underneath the zero line is going to be the area above the zero line. Now in this case, the log is actually a log base 10, so it's not natural log. So in this graph, it won't be exactly equal. The area under here won't be exactly equal to this, but you can get the basic idea. So notice that this room digs really deep, this red, and as a result, it has higher over here. Okay, this blue one doesn't dig as deep, and so it has smaller magnitudes. This green one actually digs pretty deep, and instead of being larger in magnitude over here, it's non-zero for longer. Okay, that is so that the area under the green one is the same as the area under the red one. Okay, now look at this guy. This guy doesn't dig nearly as deep as the others, but look how small this area is here compared to this area here. Okay, look how small that is. And not only that, but notice that the part underneath here, underneath the zero line, it's the frequency is way down here, whereas this one has a frequency way up here. And so it clearly looks like this area is significantly larger than this area. So how does that work? Let's take a look at, so again, here are the four plots, and here are the time responses, the step responses of the system. I think it's an initial condition response. Oh no, this is the step response. This is the output of the sensitivity function, which is the error. The error should go to zero if it's tracking properly. So here we have the different things. So notice that the red one here, which has the largest part up here, actually has the largest, takes the longest time to settle, takes the longest to, has the largest magnitude of error, and so forth. The green one actually takes as long to settle. The blue one actually settles faster and has smaller magnitudes, but it does so at the expense of not digging so deep here. And look at this kind of cyan colored one. Look at that tiny deviation. So how is it that this one is able to have such a large area down here as compared to this, and have such a tiny little blip for an error response? Well, it turns out this one does not use the same kind of controller structure as the other three used. The other three used what's called a unity feedback configuration. That is the feedback configuration I showed, where you have the loop and you have the controller and the transfer and the controller and the plant in the loop. So this one actually uses something called a 2 degree of freedom controller. Rather than having a single controller block, it actually has two blocks. One that comes in on the input and then the other that comes in the feedback. And by using a 2 degree of freedom controller, we can completely change the dynamics of how that sensitivity function works. And so you can see the sensitivity function here is actually the kind of thing that we really want. So it's very low over here, and it's very very small area here, and yet a large value underneath here. So it actually does very well in terms of the overall response of the system. It's a different type of controller design. So part of the sensitivity issue is associated with the fact that we actually have a controller that is really has the dual problems of making the system stable and providing tracking. Okay, so having those two things actually are in conflict with one another, whereas this controller the control strategy for this actually uses two controllers, one to help with the tracking, the other to help with stability. And as a result, it's able to give you a much better response, and the sensitivity function actually looks better. So we have that kind of situation. So I thought this was a good example to look at.